Hello class. In this quick video, I'm just going to summarize what you should have learned from the last two flipping physics video modules so that you have something solid to put down in your lecture notes. This is just going to be a general summary of what you need to know. Again, all of the theory behind it and all of the awesome derivations that he did with his experiments are definitely things that you should know, so always feel free to go back and watch his videos again. So what I'm just going to quickly go over is looking at the angular momentum for objects that are moving in a straight line. So as a reminder, even if an object is moving in a straight line, not rotating, we can still describe that object as having angular momentum. And then we're also going to look at what type of momentum is conserved in a collision of a particle with a board. So we have this linear angular translation is what I like to call it, basically the translation between linear momentum to angular momentum. So the big question we needed to ask was, if an object is moving in a straight line, so it's just translating, it's not technically rotating around a central axis, does it have angular momentum? And the answer was a resounding yes. What we saw was that as long as the linear motion of the object is not directed towards or through the axis of rotation, essentially there is some sort of radial distance between the velocity, the momentum vector, and the axis of rotation, then this is also going to have angular momentum. So this ball coming down this way, because its line of action is not passing through the pivot point, this ball has angular momentum, and then this ball coming in at the angle, again, since the line of action does not pass through the pivot point, it also has angular momentum. Now, one thing I do want to point out, I'm calling this the linear angular translation. This is not a conversion. The linear momentum of an object cannot be converted to angular momentum. So what's happening here isn't that this ball has linear momentum and it's somehow transforming to the angular momentum of the board. It's not like energy. Momentum cannot be transformed from one form to another. So these are not different forms of momentum. These are two very different quantities. The reason this board ends up with angular momentum is because the ball started with angular momentum. So please never write in your explanations that the linear momentum of the ball got converted to angular momentum. No, that is not true. This ball has both linear momentum because it's moving, but it also has angular momentum because it's moving at a radius, and it is just the angular momentum that gets transferred into the board. It is not the linear momentum being transformed. So do keep that in mind. So in the video, the flipping physics video, they derived this equation for the angular momentum of an object. It depends on r, which is going to be this radial distance between where this ball hits the board and the pivot point. So we have this radius. We have the mass of the object, so more mass will give you more angular momentum. We have the speed of the object. More speed will also give you more angular momentum. And then we also had the angle between r and this velocity or momentum vector. And again, this is going to be maximized when we have a direct hit at 90 degrees, minimized if we are acting through the pivot point, which would give us a sine of 0, or of 180 degrees. Now this is the equation he gave you, but there is a simplified version that I want you to know. Mass times velocity is actually just our way to calculate the linear momentum of an object. So to get to the angular version, all you have to do is multiply r by the linear momentum of the object, and of course that sine theta might matter. But that means that this equation is also going to simplify to this version here. This one is, again, you're going to apply when you know the momentum vector and the r vector are already perpendicular, which happens quite often. Then you can just multiply these two together. But if you do have this indirect hit, this momentum acting at an angle to the r vector, then you do have to take into account the sine of this angle in between. But I did want to show you this alternate version of that radial distance times the momentum instead of the mass and velocity combined together. So the big things that this equation tells you, obviously more linear momentum is definitely going to mean more angular momentum. So this linear momentum could come from more mass, or it can come from a higher velocity. Keep in mind either one of those can increase your angular momentum. Then the sine theta can also be maximized. As a reminder, 90 degrees is going to maximize sine theta. But finally, and this is where it shows up the most, the further away you are from your axis of rotation, the larger your angular momentum is going to get. So this ball coming in with this velocity through the pivot point, it's actually going to have 0 angular momentum, because notice it is heading directly towards that pivot point. If we hit this bar right here, it is not going to rotate. If we are a small distance r away from the pivot point, then we're going to have some angular momentum, but not too much. Then if we're twice as far away, really big radial distance, then we're going to have a lot of angular momentum. So this is the most common comparison you have to make, is realizing that if we hit further away from the pivot point, then we're going to be transferring a larger amount of angular momentum to the object. So when we do have this object that is moving linearly and it hits an object that is fixed and is allowed to rotate, we can also look at this in terms of momentum and whether momentum is conserved. So let's start with linear momentum, and let's just summarize if linear momentum is going to be conserved in this collision. So if linear momentum is going to be conserved, then that means the initial linear momentum of the system is going to be equal to the final linear momentum of the system. So if we have this ball of mass m coming in with a velocity v, then obviously this ball has some initial linear momentum. It is moving at a velocity. But if this bar is at rest initially, it does not have momentum. So initially, all of the linear momentum is made up in this ball moving in a straight line. Now, at the end, this ball mass system is going to begin to rotate angularly, right? It's going to hit, and then this thing is going to spin. Notice this ball no longer has linear momentum. It now has angular momentum. All of the linear momentum has been removed. So the final momentum is 0. Notice, not conserved, not constant. Now here's the big idea. It is not that the momentum got converted into this angular momentum. That is not what happened. We actually had initial momentum minus some impulse from an external force, and that gave us a final momentum of 0. So the big idea was, where did this net force come from? Because as a reminder, impulse comes from a non-isolated system. We need a net force acting on this object. Well, the fact that this bar that is hitting is basically fixed to the ground at this point, there is a reaction force, almost like a normal force, that is preventing this bar from sliding down. There is this external force from this pivot point that is essentially applying this net force over time, which is going to zap away all of the initial momentum of the system. So linear momentum, not conserved. Angular momentum, however, will be conserved. So this object coming in with momentum mv is acting at an angular radius r away. It's going to have some angular momentum. Afterwards, when it hits, the ball system is also going to have angular momentum. And the key idea here, the initial angular momentum is equal to the final angular momentum. It's really hard to show it experimentally, but the reason why, our angular momentum will not change as long as the sum of the external torques, that's supposed to be a torque, not a force, as long as the sum of the external torques on the object is 0. So this interaction right here is going to be internal to our system, and this force right here, this normal force, notice, passes right through the pivot point. So this force, while it is generating a net linear impulse because it's a force acting over time, it is not generating a net torque. So keep in mind those big differences. Not all forces generate torques, and in this situation, there is no net torque on the system, so therefore our angular momentum is not going to change. So the big thing to keep in mind, I see problems like this a lot. So I see a lot of problems like this where they have a ball that is going to collide with a rigid rod at a certain location. So maybe it's this location, or they're asking you to compare. When you are looking at this collision, you definitely want to look at momentum. Momentum. Definitely want to use momentum because for collisions, we definitely want to analyze momentum. But when we're seeing this rotational motion, just keep in mind I want to use angular momentum, not linear momentum. Linear momentum is not going to be constant just because we have this net external force that you have to be aware of, but there is no net external torque.